Okay, so we introduced Chapter 9 on Wednesday, and Chapter 9 deals with 5 different functional groups. They're all related to the carboxylic acid, right? These are 4 of the 5. The 5th is going to be the carboxylic acid, right? So we have acid chlorides, acid anhydrides, esters, amides, and then carboxylic acids. We're going to take these 4 and group them into one category. We're going to leave carboxylic acids in its own little category for now. Okay? We'll explain why later on. The important thing about these functional groups is that they are all a carbonyl functional group, and they all include some sort of leaving group. All right, so when we look at these 4 functional groups, you can see the leaving group on the acid chloride is going to be Cl minus. Right, that's the atom that leaves, and if it leaves with the electrons in that carbon X bond, then it's going to leave as the anion. Right? Here in the anhydride, the leaving group is going to be a carboxylate anion. On the ester, the leaving group is now coxide, right? So a deprotonated alcohol. And then on the amide, the leaving group is an amino group, or a deprotonated amine. Right, and this distinguishes these carbonyls, these 4 carbonyls, from aldehydes and ketones that we studied in Chapter 8. Because aldehydes and ketones, unlike these, do not have a leaving group. We don't consider them that a carbon group or a hydrogen to be a leaving group. Right? So we're going to treat these differently, and the reactions that they undergo are going to be different. So we looked at the general mechanism for these substitution reactions, and what's going to happen is that our nucleophile is represented by Y in this general scheme. Right? That's going to add to the carbonyl carbon. When it does that, rather than a direct substitution, we're going to add it, break the pi bond. Okay, when we do that, kick the electrons up to oxygen, and then in the second step, that's where we kick out our leaving group. Right, so it's a net substitution, but it always occurs through this 2-step addition, followed by an elimination. Right, and in all of these reactions that we're doing, we're creating a tetrahedral amine. Any questions about this general information? All right, so when we look at this reaction that I drew at the beginning of class today, what we have at the beginning is we have an acid chloride. And that's our electrophile in this reaction, right? And we have an alcohol. And that's going to be the nucleophile in this reaction, right? And then the leaving group is the chloride. Okay, so when we think about drawing a product for this reaction, right, we want to replace the leaving group with the nucleophile, right? And it's the nucleophilic atom of the nucleophile that's going to make the new bond to the carbonyl carbon. So in terms of the product, this is going to be the product. And you can see that the carbon-chlorine bond, carbonyl carbon-chlorine bond that was broken, got rid of the chlorine, right? And we replaced it with the oxygen of the alcohol. Any questions? Everybody sees how these two molecules are coming together? Yeah? Okay. Mechanistically, it's not going to be much different from the generic reaction or generic mechanism that we just drew out. Right, so first step is going to be addition of the alcohol, right? Nucleophile to the electrophile, carbonyl carbon. That leads to the formation of this tetrahedral intermediate. Right? You can see in the beginning of this reaction, right, we have a hydrogen on the oxygen of the alcohol. Right? In the end, that hydrogen atom is gone. Right? So we need to pluck it somewhere along during the course of this reaction. I'm going to show, so we can choose, kind of choose where we want that base to react. I'm gonna wait until the end to use the base. Right, so technically we could take this base, this triethylene, pluck this proton off and keep going. Right, what I'm going to do instead is I'm going to have these electrons fall back down, right? And then kick out the chloride leaving group. Right, so I'm gonna go through the whole substitution and then I'm gonna pluck the proton off. So we get to this protonated intermediate, and then the base is there to pluck the proton off. That's the product. Any questions about this?
Is there a reason you couldn't have just gone from the chlorine to pluck the proton off of oxygen to get it to the chlorine?
There is. So we could use chlorine. If I were to just draw this reaction out on the board, we weren't thinking about going into the lab and running it at all, right? If I were to just draw this out on the board, I wouldn't include the base, right? I would say the chloride is good enough to pluck that proton off. Practically speaking, if you wanted to actually go into the lab and run this reaction, you would add in the triethylene, right? And so that's why I'm putting it here, because we try to represent things the way we would actually do them in the lab. Okay. And we'll get into why that is, why that helps out. All right, so the key intermediate that we're gonna focus on in this reaction is going to be this intermediate, right? And so when we draw out this reaction, generic reaction, you can see that this is an equilibrium reaction, right? And I could represent substitution in both directions, right? So in the direction going to the right, I'm taking the X, that's acting as the leading group, and I'm taking the Y, and that's acting as the nucleophile, right? So nucleophile comes in, form the tetrahedral intermediate, and then we kick out the leading group, and we form these two things, okay? It's the same exact reaction, right? Just changing up the nucleophile and the leading group, same exact reaction going the other way, right? Here, if we start with this as our electrophile, Y is our leading group, X is our nucleophile, X will come in, form the tetrahedral intermediate, right? And then Y gets kicked out, and that forms these two things. So this is an equilibrium reaction. Substitution can happen in both directions. And I want to understand why, when we do these reactions, substitution is really only happening in one direction, right? So at this point, in this mechanism, right, you can see that this molecule has the option of kicking out two different groups, right? It can kick out the chloride, or it can kick out the alcohol that we just added. Right? We want to understand why, when we run this reaction, we move forward, right? We kick out the chloride, and the alcohol stays there. Okay, so I've shown this equilibrium, right? We're just focusing on this step, going from the starting materials to the tetrahedral intermediate, right, to this intermediate here, and we're trying to understand why the reaction is going forward, right, rather than going backward. And we can even draw this as an energy diagram, in an energy diagram, to show that in this reaction, right, this is going to be an exothermic reaction, so this is the alcohol and acid chloride. And then here's the ester and the chloride anion. So why is this reaction product favored? Or why are the products lower in energy than the starting materials?
Well, I guess, just a guess, maybe like looking at the entropy.
What's going on with the entropy? What do you mean?
So if you're decreasing the entropy, so it becomes negative.
No, if we can really say we're decreasing entropy. I mean, we're starting with two things, right? We're ending with two things. So, I mean, it's a substitution, right? That substitution.
Is it the elimination of the chlorine or?
Yeah, sure, that has something to do with it. What specifically?
Does it being like electron, efficient like molecule make like a cloud there, makes it higher energy or something?
So let's look kind of on the right track. I mean, electrons definitely have to do with it, right? So when we're talking about energy, usually it's the electrons, right, that we have to focus on.
Is it delocalization with that positive oxygen?
No, it's not going to be well, it's not that delocalization with positive charge. So let me try to bring this into context here. So if I take that same alcohol, right, it could be any alcohol, and I treat that with HCl, right, that's going to affect an acid-base reaction, right? So the alcohol is going to get protonated, and the chloride is going to get deprotonated. Right, and we form those two products, or that ion pair. right? Which direction does this equilibrium lie? Or how could we find out?
Hydrochloric is a strong acid. We know that strong acids dissociate completely.
Good. So pK of hydrochloric acid, anybody know? Negative what? 2. Close enough. -7. pK of a protonated alcohol. Right?
Is that
16.
16?
So an alcohol is 16. That's good, right? But this is a protonated alcohol, so this has a positive charge, extra proton, right? So this one's going to be -2. That's why I call it. Right. So when we, based upon the pKa data, right, which way should this equilibrium lie? To the right, right? It's going to lie towards the weaker acid-base pair. And we understand acid strength not by looking at the acid, but by looking at the stability of the electrons, right, after they're left behind. So here, right, this is our base, right? Over here, this is our base. Okay, you can hopefully see how similar this is to our nucleophilic substitution reaction. Okay, when we do this step here, when we show this step here, this oxygen grabbing a proton and releasing chlorine, chlorine doesn't know what's attached to it, right? All chlorine really knows is that there's something with a sigma bond attached to it, right? Just like up here, right? Chlorine doesn't necessarily know what's attached to it, it just knows that there's a sigma bond attached to it. And so this arrow that we're drawing to show the formation of chloride is effectively the same as that arrow, right? This is Bronsted acid-base chemistry, right? This is essentially Lewis acid-base chemistry, right? We're starting with a nucleophile or a base, right? And we're ending with a different base. And we have to compare the strength or the stability of those two bases just the way that we do in acid-base chemistry, right? Acid-base chemistry, we're losing a proton. In this nucleophilic substitution chemistry, right, we're losing a bigger part of the molecule. But we're still losing the same ion, right? We're starting with an alcohol, just like we are here. We're ending with a chloride, just like we are here. And this reaction favors the product because that chloride is a stable anion, right, relative to the alcohol that we're starting with, right? And so this substitution reaction favors the product because we're starting with a stronger nucleophile, right, stronger base, ending with a weaker, more stable nucleophile, right? And we can judge which is going to be the more stable nucleophile based on our pKa data, right? The same way that we assessed acid strength or base strength in acid-base chemistry. Any questions about this? Yeah.
So you're saying it's a weaker, more stable compared to the oxygen or the whole group?
Compared to the alcohol. So what we can do is we can say, all right, this is a nucleophile, right? We don't have, I mean, there's a pK of an alcohol, but if we want to understand how strong of a nucleophile this is, we have to imagine what the pK of the conjugate acid is, right? So the pKa of the conjugate acid, or what we call the pKAH, is going to be -2. Right? pKAH of chloride is going to be -7. Okay? This is telling us that the chloride is a more stable anion. The electrons around chloride are more stable than the electrons around the alcohol. Just like that same information is given to us in the acid-base chemistry. Questions? Okay, so what this means is that in order for the reaction to go forward, the leaving group has to be more stable than the nucleophile. right? So the nucleophile that we're adding has to want to be associated more with the carbonyl than the leaving group that's on there. Any questions about that? All right, so what we're going to do is we're going to look at each of these reactions. Right, and try to figure out if the column on the left are our starting materials. Right, and the column across the top, these are our products. Right, what reagents do we need to add to the reaction to get these reactions to go? Right, so obviously we're not going to try to make an acid chloride from an acid chloride. That would be stupid and waste reagents, right? So let's look at first the reaction that we just went over, right? So if we want to make a methyl ester from an acid chloride, what reagents are we going to add?
Acid chloride, and alcohol.
Good, which alcohol in this case?
Just like an alcohol attached to one carbon.
Yeah, what do we call that alcohol?
An ethyl.
No, it's
Methyl.
two carbons, yeah,
Methanol.
methanol, good. Right, so we can add methanol. Right, say we want this reaction to go really quickly though. We want a better nucleophile than methanol. Right, methanol will add, we can draw that mechanism out. Right, but maybe we want a more reactive form of methanol. More nucleophilic form.
Would that be the
What's that?
would that be the
Would that be the what?
would that be that molecule right there with the line?
Well, so if we still want to make this,
Okay.
right? So we still need to add something like this as a nucleophile, right? If we're not adding the alcohol, what's a more reactive form of the alcohol?
An ion,
Which ion?
the hydroxide ion.
Not hydroxide, methoxide, but yeah, you're on the right track. Right, so rather than adding the alcohol, we add the alkoxide. Right, this way we don't have a proton, first of all. We know that the electrons on the oxygen of the alkoxide are going to be way higher in energy than the electrons on the oxygen of methanol. Okay, and we don't have a proton to pluck when the reaction is done. Right, we just add that nucleophile, eliminate the chloride. Right, that equilibrium, because this is a much stronger nucleophile, much higher energy nucleophile, that equilibrium is going to be even farther to the right than it would be if we just added methanol. Right, so methanol will get that reaction to go fine. If we want it to go really fast and make sure that equilibrium is really far to the right, then we can add the basic form of methanol, methoxide. Right, questions? Okay, everybody's seeing how this works, right? How we're getting that substitution, what groups we need to substitute. Okay, so let's see how we can make an acid anhydride from an acid chloride. What would we need to add in for this specific acid anhydride? for a nucleophile.
Do you need to put in an ester?
An ester.
Carboxylic acid?
Carboxylic acid. Which carboxylic acid?
Huh?
Which one?
Um,
Well, so look at what our nucleophile has to be, right? The product tells you. What's that?
Methanoic acid.
Close. So ethanoic acid, right? Right. So there are 2 carbons. So that's close. Commonly known as acetic acid, right? So. Alright, so let's think about if this is going to work. Alright, so here's our nucleophile. This is our leaving group. Right, the pKa of the conjugate acid of chloride, HCl, right, -7. pKa of the conjugate acid of acetic acid is going to be probably around -10. Right? That's going to be a really, really strong acid. And so in this case, if we put in acetic acid, it's probably going to be reagent favored, right? Not product favored. And what these numbers are telling us is that these electrons are more stable, right, leading to a stronger acid. These electrons are less stable. Okay. Carboxylic acids are already acidic to begin with, right, relatively acidic. If we put another proton on them, you can imagine they're going to be really, really strong acids. Right, so this is not going to work. Right, so how could we modify our reagent to make it product favored? Okay.
Would you decrease the oxygen?
Awesome, right? So rather than adding the acetic acid, we add the acetate anion. Right, so maybe this is going to be, we'll say lithium acetate. Right, now the pKa of the conjugate acid of this is around 5, right? pKa of the carboxylic acid. Okay, and so what that is telling us is that in these 2 anions, right, the chloride electrons are more stable, and the acetate anions are less stable. Right, so in order to get this reaction to go, the only option that we have is to add in a metal acetate. Right, so this M+, that's a lithium ion, sodium ion, potassium ion, right, some metal ion. Questions? Questions? Right, if we want to make an amide from an acid chloride, okay, this would be the reaction scheme or the equilibrium scheme. Right, see if you can justify why this reaction would be product favored. Right, by by investigating the pKa's of the let's do that. Right, so what is the pKa of an amine? Do you know? Yeah.
39.
Excellent, good job, yeah. Did you remember that? You have your table open. Fine. Not as impressed, but still impressed. That's good. Prepared. And then the pK of HCl. Written it out a couple times. Right, so again, this is showing us that these electrons are less stable than the electrons left behind on chloride. Right, the thing that I want to point out, so we can fill this in up here. Right, the thing that I want to point out about this reaction is the mechanism. Right, the mechanism tells us something pretty important about this reaction. Right, so if we go through the mechanism, we're going to add the carbonyl carbon, form the tetrahedral intermediate. Right, and then we're going to kick out the chloride. Okay, and then we stop here. Right, so we need to get rid of that proton. How are we going to get rid of that proton in this reaction? What's the most likely base in this reaction? Yeah.
Would it be the amine?
Good, right? So there's a chloride in there, but we have to understand that amines are pretty basic functional groups. Right? So if there's a choice between a chloride plucking the extra proton, right, or a molecule of the amine plucking the extra proton, right, it's always going to be, or not always, but 99.999% of the time, right, it's going to be the amine that plucks that proton. Just way more basic. Right, so that changes things up a little bit. We're still making the chloride anion, but rather than that being associated with a proton, that's associated with an ammonium ion. Right, so knowing this, knowing that the amine is going to act as both a nucleophile and a base, how much of the amine do we need to get this reaction to go to the end? Get this reaction to completion.
Can you repeat your question?
Yeah, so when we look at this, right, we're trying to figure out not just the reagents, right, but how much of the reagents we're going to need. If we want to go into the lab and set this reaction up, go from the acid chloride to the amide, right, we have to figure out the stoichiometry of the reaction as well. Right, so looking at the mechanism, how many equivalents of the amine are we going to need, right? So I can say in this reaction, I need one equivalent of the acetate for every one molecule of the acid chloride, and that's going to get the reaction to go. Alexis?
Would it just be a 2-to-1 ratio?
It'd be a 2-to-1 ratio, right? And we can't get around that, right? We can't say, all right, I mean, I want you to only act as a nucleophile, but not as a base, right? Because I'm going to need you as a nucleophile, right? The amine's going to do whatever it's going to do. It's going to react the way it's reacting. Okay, and so the amine will act as a nucleophile, but whenever something acidic forms, the amine, being a very basic functional group, right, is going to deprotonate that. So if we only put one equivalent of the amine in there, we can only make 50% at max of the product, right? Because one equivalent of the amine is going to act as a nucleophile, and then whenever we form this intermediate, it's going to suck up another equivalent of the amine, another molecule of the amine. Right? So anytime we make amides from acid chlorides, we have to put 2 or more equivalents of that nucleophile in, knowing that it's going to react in both ways. Right? We can't get around that. That's the way it is. Okay, questions about that? Okay, so that's one of the reasons why when we were looking at this reaction earlier, right? When I introduced this reaction, often whenever we add in just the alcohol, we're also going to add in some amine base. Like the triethylamine that we proposed earlier. Yeah.
So I'm a little bit confused on like base catalysts, because in the first example, whenever we had like a base catalyst of the equilibrium arrow, I know that like you're supposed to have it in the beginning of the reaction and at the end of the reaction. But whenever at the end of the reaction we have a protonated form of the base, so does the base not get deprotonated at the end of the reaction?
So these are not catalysts. These
Okay.
bases, yeah, they're reagents. Yeah.
Okay.
Because I mean, even though like if we think about this reaction up here with the amine base, right? The amine base is basically pulling this proton. If this was catalytic, we would put it in 5% of the limiting reagent, right? But we have a whole equivalent of protons to pull, and so we need a whole equivalent of base to put in there. And so that's why it's not catalytic. Does that answer your question?
Yeah.
Other questions? Okay, so let's develop some more of this table. Okay, so knowing what we know about this leaving group, right, and the nucleophile we need to make the acid chloride. Can we make acid chlorides from acid anhydrides? How many people think we can? How many people think we can? Good, right? And so in this case, going from an acid anhydride to an acid chloride, we would have to install a more stable base, right? A lower energy base, right? And kick out the higher energy leaving group, right? And so that's not going to be possible. Don't have to worry about that one. All right, if we want to make an ester from an acid anhydride, what would we add? The leaving group of this reaction is going to be 1/2 of the anhydride, right? So carboxylate anion. Yep. Good. Methanol, or even better, methoxide. Metal cation. Right, so we have a slightly less reactive electrophile. So we need to add a more reactive nucleophile.
Could you essentially just draw an arrow from the top box onto the box we just drew in?
Saying that these conditions are the same as those?
Yeah, where it could be methanol, but if you want a fast reaction, it'd be the second one.
Yeah, sure. I'd say in this case, the top reaction is going to be slow enough that we're not going to really rely on that. It can happen, right? So if we were to, say, have an anhydride and for some reason it gets contaminated with an alcohol, over time it's going to form the ester. But if we were going to the lab and set up a reaction where we intentionally want to make an ester, then we would add in the more reactive nucleophile. Other questions? Okay, what if we want to make an amide from an anhydride?
Is it the same?
Same thing. much time do we have left? It's clock's
It's
a little
done.
fast, right?
2 minutes.
2 minutes. All right, hopefully you can see the trend, right? So in terms of electrophiles, the acid chloride is going to be the most electrophilic, right? The amide's going to be the least electrophilic, right? And so we're not going to be able to make the more electrophilic compounds from the less electrophilic compounds, right? So we can't make an acid chloride from an ester. We can't easily make an acid anhydride from an ester. We can make esters from other esters. We'll go over that at another time, though. Let's say more later. Right, and then making an amide from an ester. Right? You can do that again by adding the amine. Right? Here we don't need two equivalents because we're kicking out a good base that can suck up a proton. Right? And then finally down at the bottom, can't make acid chlorides from amides, can't make anhydrides from amides, can make esters from amides. All right, so this is the one exception where you can make a less reactive carbonyl, a more reactive carbonyl from a less reactive carbonyl, right? So esters are going to be more electrophilic than amides, right? And typically, we can't make the more reactive carbonyl from the less reactive carbonyl, right? But here we can. Okay, and so we would either add in an acid catalyst and methanol, right? And just add in a bunch of methanol and let Le Chatelier's principle control the equilibrium, right? Or we're going to add in the methoxide salt, a really good nucleophile, and just heat the crap out of it. Okay, and then lastly, right, we can make amides from other amides, but we're not going to really go over that reaction. Okay, questions about today? All right, we'll come back to this on Monday. We're going to probably spend another 2 or 3 lectures on this material.